Okay, so today we are going to discuss about law of large number. So here, this is an interesting fact about probability theory, where we study not only for any usual distribution, say for example that already we have introduced many distribution as a special distributions, but law of large number are applicable not only for all those distributions, but sometimes when distributions are not also specified, but only few moment conditions are specified. Okay. In most of the cases, when law of large number will be studied, then few moment condition, usually first moment, second moment, or sometime it is given in the form of 2 plus delta order moment are finite, then many law of large numbers will hold. Here, we will not make the situation so complicated. We will study two situations. One is specifically the weak law of large number. So we will study the weak law of large number, usually in short known as WLLN. Another we will study as the central limit theorem, which is in short known as CLT. Okay. Now, this weak law of large number has a special. These two are, I mean, famous by this short name, but in general, when we talk about this weak law of large number, is an example of convergence in probability, and this is an example of convergence in distribution. So first one is a convergence in probability, second one is a convergence in distribution. So can you give me one example where you have studied convergence in distribution already? We have come across in our probability lectures where we have studied convergence in distribution.
Poisson distribution.
Yeah, yes, second, please. Yes,
Poisson distribution.
Yes, Poisson distribution. So another example you have come across convergence in distribution. One example you have come across from binomial to Poisson. This is what you have already come across, and today we will see the central limit theorem as another example. Okay, so to when we will come to central limit theorem, we will talk more specifically about it. So first, let us introduce what is the convergence in probability, and then we will uh, come to weak law of large number. So first, let us define what is convergence in probability. Okay, so here we consider a sequence of random variables. Consider a sequence of random variables, a sequence of random variables usually written as xn within second bracket. As you have seen, a sequence is written in your real analysis or calculus. A similar way it is also written for n belongs to the natural number on a probability space is said to be said to converge to a random variable x, to a random variable x, again on the same space. If this thing happens, that limit n goes to infinity, probability of the collection of all such omega such that xn omega minus x omega absolute value, this quantity less than epsilon, this event is an event with probability 1 for all epsilon greater than 0. Okay. So try to see that xn is a random variable on probability space this. X is another random variable which need not be some value from xn. You can call it y or z, it doesn't matter. But xn is a random variable on omega ap. X also is a random variable on omega ap. Now, if you take the elementary event omega and collect all those elementary event omega such that xn omega minus x omega less than epsilon. And epsilon you can choose arbitrarily small. So that means they are very close. Now, if you collect all those omega and that collection is almost equal to the sample space, otherwise you will not get probability 1. So this is a event with a very high probability, then it is known as the convergence in probability. So can you give us any example where such a thing can happen? Okay, so I'm giving you this example may not be, maybe we will not proof now, we'll give the proof now. So example, let x1, x2, xn, they are IID uniform 0 theta. Okay, and theta is greater than 0. Now, max x order n, I think I have introduced this thing. x order n is maximum of x1, x2 up to xn. Okay. Then it can be shown that limit n goes to infinity, probability x order n minus theta, that quantity less than epsilon equals to 1 for all epsilon greater than 0. And that means if you take here 0, here is theta. Now if you take this is theta minus epsilon, this location, then most of the values of xn minus xn will fall here. So if you take n sample and calculate their maximum, then the value of xn will fall very close to theta when your sample size is large. That is what it means. And in inference or in statistical inference, this property is known as consistency of an estimator. So if I say that xn is an estimator of theta, then xn is a consistent estimator of theta. So we say that xn is a consistent estimator of theta. So this is the notion of convergence in probability. Eventually, if a estimator is converging to the parameter in probability, then we call it is a consistent estimate. So that is what it is happening. This proof, will you be able to do?
Sir?
Yes.
Each of the xi's are the uniform distribution, follows the uniform distribution for some set of observations, right?
No, each of xi are independently identically distribution uniform 0 theta. Yes. Now what is your query?
Like, how can we say some xi will fall only in the region theta minus epsilon to theta?
No, I am not saying xi will fall. I am saying the maximum of all these x1, x2, xn.
Yes, sir. Let that be xi. Some xi.
That will be some xi, and that value will fall within very close to theta with a very high probability.
But it follows uniform distribution, right?
It follows uniform distribution, but it is maximum of all of them. So say for example, if although it is not true, but say for example, if the score of your class may be, say, following uniform distribution between 0 to 100 for the time being, assume, but the score distribution of the first boy of your class is very close to 95. Is it acceptable statement to you?
Can we say that distribution of marks? He will have his marks.
Say yes, distribution of his marks. Yes.
So, but why will we say distribution of his marks? He will have only one mark, right? 95.
No, say that means when I say this kind of thing, okay, so let me make it clear. When we say the distribution of his marks, or that means that I am studying the feature of the distribution. Either you can say that the score of your entire class in different subjects, or I am studying, say for example, this section 4 of probability course over the years. Whoever is first, whoever is top scorer of this section, his score is close to 95 over the year. That is the meaning in that. So maybe in this year, this semester, there are 200 students in your section. Previous year also 222 students. The last to last year there was 150 students. So whatever may it be, this is a large number, and the top score is close to 95. And for the time being, if we assume that the score distribution was uniform, is it a more acceptable statement to you?
So, can you repeat the last statement?
Okay.
After,
so suppose you have that over the year, say for example, there are 200 students in section 4 of probability. Now the claim is the score distribution in your class is uniformly distributed between 0 and 100, and the top score, that means the whoever is getting highest, doesn't matter, the highest score is close to 95.
So about the distribution, will you make it for a lot of exams? Means for a lot of years.
Yes. Otherwise, I will not get the distribution of. Theoretically, I can assume something, but if I need to study the samples from different distributions, or sorry, different outcomes, then I need to check either over all the over the years, or I have to repeat the process over different subjects, but that is not a feasible situation here. That section 4 here consists of certain department students. They may not take the same subjects together. Do you get my point?
So here we take the distribution of maximum marks among all years, and we call that some X order n.
Yes, yes. In that.
Okay. Okay, sir. Thank you.
So yeah, bolo.
Sir, here in this case, xn will always be less than theta, right?
Xn will be always less than theta.
Sir, in that case, can we write theta minus xn?
Yes, that you can write. That you can. Definitely. That you can. Another example in the similar for similar thing example. Okay, so let me also introduce that one. You can see that, say for example, that say example 2. Example 2 is, say x1, x2, xn. They are following IID, say uniform. Again, for the simplicity, I am saying uniform. Say theta minus 1 to okay, theta minus 1 to theta plus 1. Okay. and I am defining, so n for the time being, you can consider 2k plus 1, and x order k plus 1 is the sample median. Okay, that means you whatever x1, x2, xn or x2k plus 1, you have them, you sort them and take the middlemost value. Now, this is also true that probability x k plus 1 minus theta less than epsilon limit, I can say that k goes to infinity here instead of saying n goes to infinity. If k goes to infinity, n goes to infinity, no problem. That is also. That means in this situation, sample median is converging to theta. So here you have theta in the middle, theta minus 1 to theta plus 1. And this is not only true for uniform distribution. If you say consider x1, x2, xn are normal mu sigma square, then also sample median will converge to mu because mu is the median there. If x1, x2, xn are IID Laplace distribution, this kind of distribution, then also sample median will converge to the population median. So here you need to take the mod because you can converge from this side or this side. In the previous case, you are converging from the lower side, but here the thing can converge from either side. So is it okay? All of these proofs are not too difficult. Okay, so for general sample median, proof will be difficult for normal or any other distribution, but for uniform, this proof will not be too difficult. And when we will study statistics, I will say something more about it. You will see there. For the time being, is it acceptable? So if you increase the sample size, the median value will be very close to, sample median value will be very close to theta. Okay, so now now we are going to state the weak law of large number as an example of, you can call also example 3, and that we are calling as a weak law of large number. And the statement is this: let x1, x2, xn be IID with expectation of xi equals to mu and variance of xi equals to sigma square, which is finite. I am not specifying any distribution. So far we have specified distribution. Now we are not specifying any distribution. Only first two moments are finite. That is given. Define sample mean x bar equals to 1 upon n sum over xi, I running from 1 to n. Okay. Then probability when limit n goes to infinity, x bar minus mu less than epsilon equals to. This is known as the weak law of large number. So in English, this statement is very popular in this way, that sample mean converges to population mean when first two moments are finite. Often people forget to say this condition, but this is an essential condition. Sample mean converges to population mean when first two moments are finite. That's it. So how can we prove this one?
Sir,
Yes,
sir, why first two moments are necessary?
why first two moments are necessary? So let us start the proof, you will understand. Okay. So what is expectation of x bar? Now, can you tell me? What will be it?
N mu.
Expectation of xi.
So that is mu, right?
N into mu.
This is n into mu, but divided by n. Is it okay that it is mu?
Yes, sir.
Okay, fine. Now, if we consider variance of x bar, what will be the value? Is it okay? Because xi is our IID, no covariance term will be there. Now, if you consider this thing, probability x bar minus mu greater than epsilon, what will be the expression here? By Chebyshev's inequality. What will be the upper bound?
Expectation of x bar minus mu whole square.
Expectation of x bar minus mu whole square divided by
Epsilon square.
epsilon square. Okay. Now, what is expectation of x bar minus mu whole square? Is it not this
Sigma square by
quantity?
n.
Sigma square by n. Now, if you let epsilon goes to, n goes to infinity. So this goes to 0 as n goes to infinity. Is it okay? This quantity. Now you see that if second order moment sigma square is not finite, we cannot say this thing. If sigma square is finite, then for large n, we can claim that sigma square by n goes to, this goes to 0 as n goes to infinity, because sigma square given as finite. If the moment, first two moment doesn't exist, then we cannot claim this thing. And that's why we need the up to second order moment is finite. Now, if you take the complement event, so limit n goes to infinity, probability x bar minus mu less than epsilon, what will be the value? Just take the complement, but here the complement will be 1 for all epsilon greater than. As simple as that. Any query? Let me know. If you have any query, you please let me know. Now you claim, give me an example of such an weak law of large number that already we have introduced in your class. Now, can you tell me an example of weak law of large number that we have introduced in your class? Okay, so let me just share the screen instead of this window. Where it is. We have already introduced. You should be careful enough to identify it. So here, this example, can you see it? This 4 diagrams. Hello?
Yes, sir.
Yes, sir.
Okay. So here, it is a very simple exercise that I have done. I have drawn 100 sample from normal 5 and standard deviation 3, then 1000 sample, 10,000 sample. And I have repeated the process 10,000 times. Each time I have calculated the sample mean, and with 10,000 iteration, I have plotted their distributions. So now here you can see that if I have 100 samples, then sample mean is that 5, population mean is 5, sample mean has its own distribution, which is given by this black PDF. Then I have increased the sample size for 1000. Then it all the true mean is unchanged, but the distribution range, you can see that it is maybe going from a little bit below 4, maybe 3.5 to 6.5, but here you can see 4.6 to 5.4. Then if we even increase to 10,000, then it is varying between 4.888 to 5.12. And if you combine these three densities, this black one, red one, and green one, then you can see that the green one has a very high peak and it is highly concentrated around 5. But red one is little bit more spread, black one is even more spread. So if you still keep on increasing n, it will be more and more concentrated around 5. So within a very small epsilon neighborhood of 5, you will have all probability. That means it will become, with probability 1, it will go to 5. So this is the idea. Is it clear?
So can you tell that by coordinate?
Say again,
What
please.
is the density coordinate?
Oh, so the density is whatever observation. I have repeated the process for 10,000 times, and from 10,000 times with repetition, I will have different values of x bar, and with that value of x bar, I plotted the histogram, and there are well, that density curve I have obtained through the software package, and that density is obtained with this command, density of sample mean 3 or sample mean 2, sample mean 1. So this density curve you can get by a smoothing out of this histogram. And there are different density estimation method. Usually R use the kernel density estimation method with smoothing function as the normal standard normal density function, and with that smoothing we get the density curve. Have I answered your query?
No, sir. I was asking the density. Is it some PDF or?
Yeah, of course, density is a PDF. Whenever I am saying density, so this is the density, say for example, 100 observation from normal distribution. So this is the density with mean 5, variance sigma square by 100. This is the density with mean 5, variance sigma square by 1000. This is the density with mean 5, variance sigma square by 10,000. So each time the mean part remain unchanged, but the variance part is going to 0 gradually, and when the variance is going to 0, you will have all probability assigned to the mean only. Is it okay?
Yes, sir.
So this is the idea of weak law of large number. Now, having said that, can you give me the example which you have already come across in this course for weak law of large number? So can you recall that example?
So that T statistics you showed in class,
Which one? Which one? Please say.
last class, and T statistics you showed. In that one, x bar goes to normal mu sigma square by n. So
Yeah.
in that n tends to infinity, the variance will go to 0.
No, that is not exactly, well, that is not exactly the thing. That will come under the distribution of convergence. That T distribution, when n goes to infinity, will converge to normal distribution. So that thing we have demonstrated here. Yeah. So degrees of freedom increases. Now, if you keep on increasing the degrees of freedom, T distribution will converge to normal distribution. That is a little bit more delicate situation, but that this is convergence in distribution. The weak law of large number I have introduced to you in a very first few lectures. Yeah, here you can see. With I have this estimation of value of pi. I have increased the sample size. Initially, when you use the small number of samples, then the fluctuation will be there. But as you increase the sample size more and more and more, the fluctuation will be going to 0 and it will converge to the true value with a very high probability, and that is going to be 1. Is it clear? If you take 5, 10 samples, 20 samples, 100 samples, there will be fluctuation. But as you keep on increasing the sample size, the fluctuation will going to slow down, and finally you will converge to the true value with probability 1. That is what was introduced and in the very beginning, and as you take larger and larger sample size, you will be able to estimate the value pi by 4 here with a very high probability correctly. Is it clear? Hello? Hello? And a similar example you have for this one also, when you estimated the value of E from the data. Here you can see with small sample there are fluctuations, but as you keep on increasing the sample size, the fluctuation going to 0. And that is what it means by convergence in probability. Any query? So again, if you take small sample, there will be ups and downs, but if your sample size is large enough, you will be going to the true value with probability 1. So is it okay with all these examples? And
Yes, sir.
okay, so now after this weak law of large number, let us go to the central limit theorem. So first let me give you the statement and of it. So for central limit theorem, we need the idea of convergence in distribution. So a sequence of random variable xn, n belongs to the natural number, on probability space omega n fn pn is said to converge in distribution to x on probability space omega fp. Remember that for weak law of large number, when we have talked about convergence in probability, everything was in the same sample space. Xn and x, they were in same probability space, but now we need not require that this omega n fn p are same as omega fp. They can be different. Okay. So now what we are saying that the sequence of random variables are on the probability space omega n fn p, and another random variable x on omega fp. Then if it happens in this way that the limiting CDF of xn, so as n goes to infinity, you consider any real number a, f of xn of a and f of y of a. You can get the f of y of a as a limiting value of f of xn of a for all the point a where fy is continuous. Then we say that xn is converging in distribution to y. Converging in distribution usually denoted by this notation: xn arrow at the top of the arrow d converges to x. And it is an interesting observation or theorem actually, that if xn converges in probability to x, then it implies xn converges in distribution to x, but the reverse is not true. these proofs and counter examples are not in your syllabus. It is either you will study in inference course or in advanced probability course. But you, for the time being, you can keep this note. And if xn converges to x in probability, then h of xn converges to h of x for any continuous function h. So these are very strong results. So we are not going to prove any of them, or not even going for any example for the time being. So here, what is our claim? First, try to understand when we say that convergence in distribution, that means the CDF of xn converges to the CDF of y. Already you have seen convergence in distribution from binomial to Poisson. There it is easy to demonstrate through PDF. So we have demonstrated through PDF or empirical PDF, but the demand is that the CDF of xn converges to the CDF of y wherever the y is continuous. So that will be the idea, but this convergence in CDF can also be obtained through the characteristic function or moment generating function if exists. So characteristic functions are just one step extension that expectation of e to the power itx, where I is the complex imaginary number. Moment generating function, you remember, e to the power tx. So instead of mxt, they write as sorry, I have to correct it. Xn I have to write here. Xn I have to write. So if the expectation of e to the power itx or e to the power tx, if you take the expectation and then you let it converge for n goes to infinity, and if the limiting value of the function is a known or some suitable moment generating function or characteristic function of a random variable, then we can say that xn is converging to y. So we will use the moment generating function for our purpose. Characteristic function is not in our syllabus. So is the idea clear?
Sir, in the convergence and distribution, what is y, capital Y?
Okay, capital Y is another random variable. Xn's are some other random variable. So let me give you example and one by
Sir,
one.
in the convergence PDF, sir, I'm getting confused between capital X and capital Y.
Okay, so okay. Those are nothing special. They are dummy variable. I'm coming. So here, whenever I am saying, well, I think I had done a typo. So I should write here. Either I have to write y here or x here. Sorry, I think I had a typo. I will change it.
Oh, okay, sir. Okay, sir. Now it's clear.
Okay, so for an easy example, so convergence in distribution so xn converges in distribution to, say, let us call y, then f of xn of a limit n goes to infinity, f of y of a for all a where fy a is continuous. This is what is the claim is. Now that same thing we can also obtain which we can also obtain by showing m xnt converges to myt. Okay. So if this thing holds, moment generating function of so limit n goes to infinity. If the moment generating function of this quantity xn converges to the moment generating function of y, then we can claim this thing. But the most of the cases we don't do the proof through moment generating function. We use or limit n goes to infinity. So phi xnt, which is nothing but m xn it converging to phi y t, which is m y it. This is nothing special. So this is either this is by mgf or by characteristic function. Okay, so this is not in our syllabus, so we will go by this. Our aim is to get this. So for an easy example, and not any difficulty, so let xn follows normal mu plus 1 by n sigma square plus 1 by n square. Okay, I will just superficially constructed this. So where xn will converge in distribution as n goes to infinity?
Normal mu sigma square.
Normal mu sigma square. So if you just see that if this is the curve of, this is for normal mu sigma square, then if your n is 1, then it will be, if this is mu and this is, say for example, mu plus 1, then this will be normal mu plus 1, but spread will be even more because variance is sigma square plus 1. Now if you take mu n equals to 2, it will gradually shift little bit, variance will be little bit less. If you take mu equals to 3, then it will again shift little bit, variance will be less, and in that way ultimately it will fall on this green curve. A green curve will fall on this red curve and it will become normal mu sigma square. So this is how it will look like. Is the idea wise it is clear? Any query? So already another example already you have seen that xn follows binomial n pn and n into pn goes to lambda as n goes to infinity, then xn converges to y, where y follows Poisson lambda. This is a known factory. Okay, so the notation is xn converges in distribution, or also people write small d, capital D, both are acceptable, or Xn converges in law. Sometimes it is written in this way, converges in law to Y. This is also a notation, a standard notation, followed by the different. Now, another special example of convergence in distribution, we can call it a central limit theorem. So first, let me state the theorem and its interpretation, then we will prove it. Usually known as CLT. Let x1, okay, there are many versions of CLT. This is what is in your syllabus, what I'm writing. x1, x2, xn be IID random variables with expectation of xi equals to mu and variance of xi equals to sigma square, which is finite. Then define Sn equals to sum over xi I running from 1 to n, which is nothing but n times x bar, you can easily see. And Tn, let's look at it carefully. Tn is Sn minus n mu divided by sigma times root n, which is nothing but you can also write this thing as root n x bar minus mu divided by sigma. So here you can see that what I have written here is Sn minus expectation of Sn divided by square root of variance of Sn. Okay, and it is same thing, x bar minus expectation of x bar divided by square root of variance of x bar. Check whether these four quantities are same or not, it is acceptable to you. Is it okay? Please check. Students often do the mistake like this. They write Sn here, then write sigma square by root n here. Or they write x bar here and sigma square into root n here. Students often do this mistake. Don't do this mistake. The idea is very simple. Whatever variable, random variable is here, subtract its own mean, scale it down by its own standard deviation. If it is Sn, it is expectation of Sn, it is square root of variance of Sn. If it is x bar minus expectation of x bar divided by the square root of variance of x. Is it clear? Now, if this is defined, then limit n goes to infinity, probability Tn less than t equals to capital phi t, which is the CDF of standard normal distribution. That means minus infinity to t e to the power minus half x square, okay, sorry, x square root 2 pi dx as n goes to infinity. So that means Tn converges in distribution to normal 0. Or rather I should, okay, so, okay, with little abuse of notice. So this is the claim. Is it okay?
So we
Remember,
are just
say
stating
yes.
the result. We are just stating the result, right? We are not proving it.
No, I will prove it.
Oh, okay.
I will prove it.
This is not the proof, right? This is
No,
just
this is the statement. This is
okay.
the construction and statement.
Okay.
Remember, xi's need not be normally distributed. They just need to satisfy this first two moment condition. Xi's need not be normally distributed. For any distribution, you start with first two moment finite. Take the IIT sample. If you standardize it properly, you will have normal distribution as a limiting distribution.
Sir,
Yes.
can you explain this Sn minus n mu n by sigma root n? How is it equal to Sn minus expectation of Sn by root or Vs? V of Sn shall be n square sigma square, right?
N square sigma square. N square sigma square, yes. So square root of that is sigma into root n. Sorry, not n square sigma, n sigma square. Hello? Am I audible?
Yes, sir.
So it will be variance of Sn is variance of sum over xi. So sum over variance of xi as their IID. So n times sigma square, right?
Okay, so yes, sir.
Alright.
So it is n square V of x bar.
Yes.
Okay.
Sir, how are you writing phi t to be equal to minus infinity to t e raised to power minus half x square by root 2 pi?
So this is the CDF of standard normal distribution.
Yes, so how is it equal to that, sir?
Do you remember what is the PDF of normal distribution?
No, sir, I'm saying this when n tends to infinity, p of tn less than equal to t.
Okay. No. This thing we have to prove. This is the claim
Okay.
of the statement. Okay. So
Okay.
okay. So this define this. Okay. Then I should write then limit goes. This is the claim of the theorem. If you have this construction, then this should hold. Okay. So first of all, let us see in diagram so that we get convinced that whatever we are claiming is okay, and then we will go for the proof. Oh no, not this one. Yeah. Okay. So here, CLT. Okay. So now here from binomial distribution, I am calculating. Data are collected from binomial distribution. Then square root SS is given as the sample size, mean of the data minus n times p divided by square root of n into p into 1 minus p. Then this is constructed as z, and then the distribution of z is plotted. So data are collected from binomial n is 23, p is 0.7, 100 samples are collected. So our n in the theorem, here n is in this code, it is SS, sample size. Okay. So, and I have repeated the process 10,000 times. So the data are drawn from this distribution, but with that standardization, you have the CLT, and the red curve is the PDF of standard normal distribution, and the blue histogram are the histogram of this Tn that we have defined from binomial distribution. So you can see that it is a skewed distribution, but this one is a very close to the standard normal with centered mean 0, variance 1. Similarly, if you generate data from Poinsot distribution, again I am using sample size 150. Poinsot lambda is chosen to be 1.5. So the data are drawn from this highly skewed distribution Poinsot. with 150 observation, again with proper standardization, sample mean minus the population mean divided by the its variance, that is square root of lambda multiplied by root n, which is square root of SS. So with this standardization, again you can see that it converges to the same distribution, standard normal distribution. And the last one from exponential distribution, here also I have chosen lambda equals to 1.5, same sample size. Again, exponential distribution is highly skewed, but again with the standardization you will get the central limit converging to normal. So you need not worry that whether the distribution has to be symmetric, the original distribution has to be symmetric, or it has some other well-behaving property. No, nothing required, only first two moments are required. With the standardization, you will obtain the CLT for large sample. So is it convincing that it will hold? I think nothing left to show. Now let us go for the proof. So before giving the proof, let me just tell you an interesting fact here, that have you heard the term entropy? In definitely not in this probability course, but have you ever come across the term entropy or uncertainty?
Yes, sir.
Okay, very good. So entropy is a measurement of uncertainty, which is given, one of the measurement is given by Shannon. So it can be, if just let me give you this statement, it is far reaching for us at this time point. So if say Z and W are two random variables with expectation of Z equals to expectation of W and variance of Z equals to variance of W. Two random variables with first two moments are same. Okay. And Z follows normal distribution and W does not follow normal. Some other distribution, doesn't matter. Then the entropy of Z is more than the entropy of W. That can be shown. Okay, proof needed. Proof is not too difficult, but well, if time permits, someday we will do it. This is a very important observation. Why? Because in nature, when large number of population gathers, maybe say bacteria, fungus, human, or any other species, when the large number of population gathers, nature always try to increase the uncertainty or the variation in the system. Why? Because if there is more and more variation in the system, then the vulnerability is less. This is a natural law. That means if in our genetics or maybe our in day-to-day practice or more specifically our physical phenomena, if the variation or uncertainty is more, then some virus or bacteria or some animal will come and kill us. All the species, not only human, any species, that chance will be less. So it is a natural tendency when large number will gather in such a place, then nature will try to increase the uncertainty of the system such that the vulnerability of that species or the system become less. And here, if I have just stated that if you have two random variables, one is normally distributed, another is not normally distributed, and they have same mean and variance, then it can be shown that the normally distributed random variable has more uncertainty or more entropy rather, and uncertainty is measured in terms of entropy, more entropy compared to the non-normally distributed random variable. So that is another philosophical reason why this CLT converges to normal distribution rather than any other distribution. Because this distribution, normal distribution with fixed mean and fixed variance, here it is typically 0 and 1, has more uncertainty or more entropy compared to other random variable with fixed mean and fixed variance.
Sir, how do we compare entropy of two random variables?
Okay, so for Shannon gives a measurement of entropy. There is a formula, so which is, if I am remembering correctly, expectation of minus of log of fx, if I am not wrong, if I have not forgotten. So usually I think it is given as h of x. So what you need to do, minus of log of fx into fx integration dx. This is the measure of entropy. Okay, you just search in Wikipedia entropy, you will get so many things. This is the formula given by Shannon. Okay, and in most of you are, or half of the class is from computer science department, you will come across this entropy measurement very frequently in your system, in your course. Okay, if time permits, someday we will come to it, but for the time being, just let me state that this is one of the philosophical reasons, and not only that, all these kind of proofs and everything are available in one research paper, most probably published in 1982. So, and that is not, that requires many more things, and also statistics. So this is the idea behind everything. So now let us go for the proof. So we have seen the example, we have got the philosophical idea, we have the construction. Now just let us prove it and conclude the session. Any query before we start the proof? Okay, so let us start the proof. Proof of CLT. Okay, now let us see few conditions maybe we need it. Okay, so first of all, x1, x2, xn are IID. Not, yeah, they are IID with expectation of xi equals to mu and variance of xi equals to sigma square. Okay, now what we have defined, Tn equals to Sn minus n mu divided by root n sigma square. Okay, so what?
Root n sigma.
Sigma. Sorry. Sigma. Now let us write Sn explicitly, sum over xi I running from 1 to n minus n mu divided by root n sigma. So I can also write this thing in this way, 1 upon root n sum over I running from 1 to n xi minus mu by sigma. Is it okay? Okay, so if this is so, let us define yi, which is xi minus mu by sigma. So it is trivial to note that expectation of yi equals to 0, variance of yi equals to 1, and yi's are IID. This up there, I can say yi's are IID. Is it acceptable? If, and with this notation, I can write this quantity as sum over I running from 1 to n y. Any query? Okay. Note one thing, that expectation of Tn. What will be the expectation of Tn?
Zero.
0. Variance of Tn?
One by n.
Ah,
Square root n.
oh man, why you are doing so mistake?
1.
Yeah, I have just calculated the variance of this here formula. Now you should not do that mistake. The variance is 1. So if you see Tn by construction, either you go by this expression or by this expression, doesn't matter. Expectation of Tn equals to 0, variance of Tn equals to 1. So that is trivially true. Now the beauty of CLT is that it is saying that Tn will converge in distribution to normal 0. This is the added thing claimed in CLT. Mean 0, variance 1 is trivial. But what the beauty of CLT, that it is saying that Tn converges in distribution to normal with mean 0 and variance 1. Okay, so that is the main fundamental thing that we can have. So now, and we will prove it by, we will show it by moment generating. Okay, so what will be the MGF of Tn? So MGF of Tn is expectation of e to the power small t into Tn. Okay, let us go by the routine definition. Expectation of e to the power t by root n sum over yi and as they are IID, at least independently distributed first, then I running from 1 to n m of yi t by root n. Check whether all those stuff are acceptable or not. Then as they are IID, so this is for independence. This product splitting. Now as they are IID, that is m of, I can just take y1 t by root n whole to the power n, and this is because of identical distribution. and then I can, this expression I can split over the formula k running from 0 to infinity m of y1 0 with kth order derivative t by root n whole to the power k by k factorial, this entire summation to the power n. So this expression you can get from the moment generating function that we have defined already when we have done it. So just from the E series, and then power is n, everything. Yeah. So now we need to be careful about what will be these expressions. Then we have to truncate it. So let me just copy this thing because it will be needed. Once again, expectation of e to the power t of tn, which is sum over k running from 0 to infinity m y1 evaluated at 0 kth order derivative t by root n whole to the power k divided by k factorial whole to the power n. Okay, now let us have some, what will be the m of y1 t, m of y1 t, that means expectation of e to the power y1 t. Okay, so now if you go by m of y1 t, what will be m of y1 evaluated at 0?
One.
1. M of first derivative of y1 evaluated at 0? What you are supposed to get? If you take the first derivative of moment generating function and put mu equals to and put t equals to 0, what you are supposed to get?
Expectation of y.
Expectation of y, and what is that?
0.
0.
0.
Yes, correct. M of second order derivative of y1 evaluated at 0. Second order derivative evaluated at
1.
0, 1. Okay, so that much is needed. We will truncate after that. So whatever term, here you can see that the first term will be for m y0, then m, so rather I should write m0, no derivative, one order derivative, two order derivative, and rest part we will truncate. So here this expression I can write in this way, that so instead of t I have t by root n. That thing I need to take care. So first term 1, second term 0, t by root n whole square, that means t square by n, 2 factorial, that is 2, Rest part I am considering as a residual in the form of t by root n whole to the power n. Okay, so here I define that residual part t by root n, r of t by root n is this term from k running from 3 to infinity m y k or y1 k evaluated at 0 t by root n whole to the power k by k factorial. Now it can be shown, I am not going for the details here, that limit n goes to infinity, r of t by root n whole divided by t by root n, this is also going to 0, and not only that, limit n goes to infinity, r of t by root n divided by 1 by root n whole square, that quantity will also go to 0, and so in that way we can neglect all these terms. So you are left with this expression. So now if I take the limit n goes to infinity, expectation of e to the power t of tn, which I can write as limit n goes to infinity 1 plus, I am taking 1 upon n outside, then I have t square by 2 plus n here r t by root n, okay, multiplied, this bracket close, this bracket close, whole to the power n. Now again I can rewrite this thing in this way, limit n goes to infinity 1 plus 1 by n t square by 2 plus r of t by root n whole divided by 1 by root n whole square. This n I am writing in this format. This quantity close, whole to the power n. Now if you take the limit, this entire quantity is supposed to go to 0. This part will contribute. Here is 1 upon n. So as a as a limit, you will get e to the power t square by 2, and which is the MGF of normal 0. So then we claim that Tn converges to Z, where Z following by continuity. So this is how the proof goes. In advanced courses or any book, most of the book they follow characteristic function. So here you, instead of, if you use characteristic function, you will end up with e to the power minus t square by 2. So I square will come, so that will give you -1 if you use characteristic function. If you use moment generating function, this is the way the proof goes. So I think I am done with it. Any query? Or we can have one small, okay, 2 minutes time we have, so we can have a very small exercise. So this one. Oh no. What? No, I closed it. Yeah. This is Find the limit. Limit n goes to infinity, e to the power minus n, sum over k running from 0 to n, n to the power k by k factorial. Tell me, this is as an application of CLT. From where will you start? Any guess before you start? What should be the limit?
One.
No. So can you identify any distribution seeing it? First of all.
Poisson.
Poisson, correct. Poisson, correct. Poisson with parameter?
N.
N. Okay, very good. Now you are halfway done. So if I say that in this way, so xn, or rather let say, if I say Sn is following Poisson n, so what is this? This is nothing but limit n goes to infinity, Sn less than equals to n. Is it okay? Is it okay? 0 to n. So Sn less than equals to n.
Yes, sir.
So now I can formulate in this way. Let xi's are IID Poisson 1. Sn is sum over xi, I running from 1 to n. Is it okay? By the additive property of Poisson, Sn will follow Poisson n. Now what is the expectation of Sn? N. Variance of Sn? N. So limit n goes to infinity, probability Sn minus n divided by square root of n less than equals to n minus n divided by square root of n. Any trouble? So limit n goes to infinity, probability Sn minus n divided by square root of n less than equals to 0. Now you tell me what will be this one?
Half.
Half. Done. Okay, so before we leave, let me know that whether you want some more problem solving from the next week, or first let me cover the statistics part and then problem solving.
So I think problems first would be better.
Problem first will be better. Okay, so one day Monday we will do problem, and then Tuesday we will start statistics portion. Okay, thank you.
Sir,
Yeah, voila.
sir, can you go to the page where you have discussed x, nth order x and nth order x?
Okay.
Yes, sir. Here it is following the uniform distribution, right?
Yes, x order n is not following uniform distribution. Individual xi's are following uniform. X order n will have some different distribution.
Okay.
That derivation we have done in the class. From there you can get.
Yes, sir.
Okay, so Monday we will solve some problem and then we will proceed for estimation. Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you, sir.